Hello everyone, today we are continuing our topic of operational amplifier by looking at their application as linear amplifiers. So we're going to look at voltage follower circuit using op-amps and the weighted summer circuit using operational amplifiers. So the first circuit that we're going to look at is a voltage follower. If you look at this, the circuit configuration with this op-amp, the output is connected to the negative input terminal of op-amp. That means you have negative feedback. So that means you can use the second golden rule of operational amplifiers, which states Vp is equal to Vn, and because Vp here is equal to Vi, so source is connected to input signal is connected to the positive or non-inverting terminal of op-amp. That means Vn at node voltage at negative or inverting terminal of op-amp is equal to Vi, and on the other hand, Vout is also connected to the inverting terminal of op-amp. That means Vout is equal to Vi. So output voltage follows the input voltage, and hence the name voltage follower. So as you saw before, op-amps have the benefit of having a very large input impedance and very small output impedance. And specifically for this configuration, the input impedance Ri is equal to infinity, because Ri is defined as Vi divided by Ii. And this is my II input current, and II is equal to infinity, equal to 0, so there is no current goes to the op-amp. So as a result, this input impedance is equal to infinity, and the output impedance of op-amps is equal to 0. So this configuration which is the same as non-inverting op-amp configuration. The input signal is connected to the positive terminal input, and the negative feedback is present. So in this configuration, input impedance is high, output impedance is low, and generally they are used as buffers for situations like when you have a source with high output impedance and load with low impedance. So because their impedance doesn't match, the source and load doesn't match, you can use a buffer in between. You can use a buffer to connect that source to the low impedance load without suffering the impedance mismatch between source and load. So, and the other configuration that we're going to look at today is the non-inverting summer. So first let's check. There is a negative feedback here. Output is connected through this RF feedback resistor to the inverting terminal of op-amp, so there is negative feedback present in this op-amp circuit, and two input signals V1 and V2 are connected to the positive terms through resistors R1 and R2 are connected to the positive input terminal of op-amp. So this operates in the non-inverting configuration, so output and two inputs are going to be in phase. What else? So I'm looking for an expression like this. Vout is related to V1 and B times V2. These are coefficients that I'm going to determine by solving this op-amp circuit. So it's a linear output is linearly related to V1, voltage source 1 and voltage source 2. I want to figure out what these coefficients A and B are. So to do so, we already figured out that because number one is golden rule of op-amp golden rule number 1, which states In is equal to Ip, that's equal to 0. For the case of ideal op-amp, these two are equal to 0. Number 2 is that because I have negative feedback, Vn is almost the node voltage at the non-inverting terminal is equal to the node voltage at the inverting terminal. So Vn and Vp are equal. Now we are going to use the node voltage analysis method to find this expression and calculate the A and B coefficients. So let's write the KCL at node P. If you do so, you're going to have Vp minus V1 divided by R1 plus Vp minus V2 divided by R2 equals to 0, because Ip is equal to 0. So the other one is at node n, Vn divided by Rs plus Vn minus Vout divided by Rf equals to 0. Again, In is equal to 0. From here, I have an expression and I have an equation that relates Vp to V1 and V2. So if I factor out Vp from this equation, from the left side, I'm going to end up with 1 over R1 plus 1 over R2. That's going to be equal to V1 over R1 plus V2 over R2. And from here, I have an equation that relates Vout to Vn. So Vout is equal to 1 plus 1 Rf over Rs multiplied by Vn. So I'm going to use that to simplify these two equations to find an expression that relates Vout to V1 and V2, because this Vn and Vp are equal. So if you do so, you're going to have Vout is equal to 1 plus Rf over Rs divided by 1 over R1. So it's going to be 1 over R1 plus 1 over R2 multiplied by V1 over R1 plus V2 over R2. As you can see, we found an expression that relates Vout to V1 and V2. So we achieved our. So this op-amp circuit configuration is the weighted summer configuration and non-inverting weighted summer. They're usually utilized in different applications, including in the design of audio systems. They can be used to mix signals from different musical instruments, for example. This kind of circuit generates an output that's a weighted sum of V1 and V2. So we can also have the weighted sum in the inverting configuration. So Vout is in this configuration. Vout is going to have pi phase shift V1 and as well as V2. So we can write the KVL, the node voltage, use the node voltage analysis to find Vout with respect to V1. So it's going to be negative A1 times V1 minus V2. So let's write it this way. Vout is going to be negative A times V1, negative B times V2. So the coefficients are negative, have a negative sign, and it's again linearly, the output is linearly related to V1 and V2. So I'm going to use the node voltage analysis method to calculate the coefficients in this expression. So at node n, this Vn, I can write Vn